Okay. Okay. So thank you all for coming. And so today we have our speaker Victor. So Victor, I think he joined us at Rutgers in 2015, 14, 16. Okay. Okay. And he's an undergrad at University of Montreal. Is that correct? Okay. So and he joined us with a doctoral fellowship with the Quebec government, and he's also currently the recipient of the Meritech Fellowship for Quantum Field Theory. So today he's going to tell us about this ARPES on high DC cuprate. So yeah, take it away, Victor.
Thank you, Tsung-Chi. Yes, there's two pronunciation for my alma mater. It's either the English one, which is University of Montreal, or Université de Montréal in French. But you know, I'm not going to expect anybody to get that right. Okay, so I'd like to talk about the ARPES. The ARPES technique in general. You know, it's going to be a brief overview of what ARPES actually is and how it's so amazing to connect with the theorist's mind and electronic dispersion. Okay, so really, this is in the same format as all the S-bars, right? This should be an informal format. Just really interrupt me and ask me questions. I hope, even if it's something that's like a tangent, let's go toward a tangent. Let's go down the rabbit hole. That's just for the fun of it, okay? So without further ado, let's begin, and hope that we can finish before the town halls tonight. I'm joking. Okay, so let's introduce first ARPES. So ARPES starts with this essential concept, this very simple concept of the photoelectric effect, right? Photoelectric effect, what happens is you shine light onto a material and collect electrons that are expulsed from it. So and this does not depend on the intensity of the ray of light that you shine on it, but rather only on its energy, right, h bar nu. So nu being the frequency. So if I shine light onto this material, I will eventually collect a certain amount, a certain intensity of electrons being carried out. And this is a famous plot that you see when you're doing your undergrad physics, is if you're plotting on the x-axis the light frequency versus the electron kinetic energy, you really see quickly that if you have a certain frequency that is less than a critical frequency nu naught, you will not release any electrons. That's because there's a finite binding energy of the electrons in the material. And if you don't have enough energy in your photons to kick it out of that particular energy, they will not be able to fly away. So that's and that element, I'm trying to navigate this new annotation. Okay, good. And that concept of this binding energy makes it so that you can, if you understand well if you can know what the frequency of the photons that you send onto your material, and you can know very well what is the energy of the electrons that come out, you can know exactly what is the energy that was required to release them from their position deep into the material. So, and knowing that energy is really critical to understanding what happens deep into the materials. Okay, so what you're trying to find out is this work function phi here. It's just the energy to delocalize the electron from the surface. When it's deep embedded into the surface, this work function really takes it out and makes it fly away, and with some kinetic energy. So how ARPES works is in this kind of in the lab is by sending this ultraviolet light source, by sending these very focused light beams towards the sample over here. And then you have this electron spectrometer here, which is a chamber that collects the electrons. There's some magnet in there that makes them rotate around, and you're able to analyze what is the energy of that electron collected. A big important aspect to it. Oh, this is annoying because, okay, I see. You can clear all your drawings. Okay, all right. Oops, there we go. An important fact that ARPES works with is the fact that you have to, this energy, this kinetic energy it comes from the conservation of energy in your system, right, from the photoelectric effect. But using the other law that's super important is conservation of momentum, right? The photon momentum needs to be carried out by the electron momentum out of it. If you measure both the direction of this electron coming out with respect to your photon coming in, right, you can know whether the momentum of what you're collecting is different, and you can know whether whether the vector is different, right? If the parallel contribution has changed. If you know both the momentum and if you know the energy, you'll know the pretty much everything you need to know about the electron behavior. So you're sending your photon in with a certain momentum and with a certain frequency, which then is able to kick an electron out of a specific momentum corresponding to the momentum of the photon you just sent. And essentially what that allows you to create is the dispersion of the electrons. So you're able to get the full energy versus momentum in the electronic system. And this is something really that you want. So these two sets of equation is really what ARPES works with. You're collecting, you're measuring the kinetic energy of the outgoing electron, you're measuring the angle of emission, and from that you can extract the binding energy of the electron in the metal and the crystal momentum of that particular electron at that energy. And what that leads to is that this is the really important concept in condensed matter physics is, just give me a second.
It's oven.
It's okay. I'm done. Yeah, it's good. I'm back. I just had to shut off my oven. Okay. So what this leads to is that you can collect information on the energy versus momentum of the electrons. And why is that an important thing? Is because that's the main information we can gather from a lot of theoretical predictions on how our basic models for materials are really electrons moving around in a. We consider all of the cores, all of the ions to be non-moving, to be static to where they are, and we consider the electrons, the valence electron, to be flying around in the material. And there are many techniques such as ab initio technique and density functional theory are able to understand why, like how these electrons are going to move around in the material, and they're able to predict the energy levels of the electrons with respect to their momentum. And what this creates is these band structures. Right? This is just a band structure for, I think, silver, if I remember correctly from Google. But it creates these band structures, and what you're able to do with ARPES is really get these specific levels close to the Fermi level here, which is, I think, 5, because this is where mu is, and you're able to obtain the dispersion in the experimental material. So you're able to kind of compare what your prediction is for this material and the band structure versus the theoretical. But you're able to compare the theoretical prediction of the band structure with the experimental realization and obtaining the band structure. So that can be a very powerful tool if you're able to measure it and to see whether there's deviations from it, from maybe your ab initio treatment didn't incorporate enough things. Maybe you didn't, you're missing bands, you're missing things like that, or maybe something even more stronger than that, is something like a many-body effect, an electron correlation effect, could radically change your band dispersion. So ARPES can go in and see whether that can that appears.
Can I ask a question?
Yeah, go ahead.
So this ARPES can only measure the metals, right? Or can you measure insulator? Or
I mean, you could do it in an insulator, but the insulator has a huge gap. There's a reason it's an insulator, is that there's a really massive gap. So if there's no state at in the middle of the gap, you will not see anything in the case of ARPES. In recent years, there's a lot of study of topological insulators, right? Topological insulators are special because they have surface states. So they have a density of states. They have levels that are solely on the surface. So if you do, so there is some states in the insulator gap that you could see using ARPES, and you can actually see them. And ARPES has been a very useful tool for these topological insulators. But I think if you just did ARPES on a normal insulator, you wouldn't see much. I think it would be a rather bleak endeavor.
Agree.
Yeah.
I got a quick question, Victor.
Yeah, go ahead, John. Yeah.
Could you go back to the last slide?
Mm-hmm.
What's the x-axis on this plot?
X-axis is momentum. So
Okay.
this is crystal momentum, and these are all different, very high symmetry points in the crystal. So there's always symmetry at these points that is, enforces degeneracy of certain levels. But if I could, if I can add here, that should be, there we go. White, it should be, let's get back. So this is really my momentum, and it's momentum, not just like, momentum is in a three-dimensional material is going to be a three-dimensional vector. This is momentum along some particular direction. So in the Brillouin zone, this is going to be along the W to L line in the Brillouin zone. So it's a complex construction that's made easier for us to visualize than dispersion in for different three-dimensional momentums.
Got it. Okay, cool. Thanks.
Okay. So, like I said, we get because of the photoelectric effect, we're able to pluck an electron right out of the material. So we're able to get this energy versus momentum of the particle. Now, if you might remember that in the equation I just showed before, and there we go. The momentum conservation equation is really a momentum conservation in the longitudinal range. Okay, so if I send the photon kind of goes in towards the surface, bumps on the surface, and the electron goes out, there's not a conservation of transverse momentum. So momentum in the z-axis, let's say, perpendicular to the surface of the material, is not conserved. And that has always been kind of a limitation of ARPES, is that there's no information about the perpendicular momentum to the surface. So there's no information about the dispersion for momentum changing as you go deeper into the material, in some sense. So, this also means that the study for three-dimensional systems is a bit more difficult, because for 3D systems, you'll have to find a good surface on which you can cleave, right? If the surface has too much asperity, is too much fluctuation on the surface, it's going to ruin your ARPES data. And so you need to find a clean surface, and most 3D materials have only a certain subsets of really clean surfaces on which you can do ARPES. And you're always losing that K perpendicular, so reconstructing a whole Fermi surface and a whole the whole behavior of the dispersion of the electron for 3D materials is not as easy as in 2 dimensions. In 2 dimension, well, there's no need for a 3-dimensional vector, that the momentum that is perpendicular to the surface. There's only a in-plane momentum, so you're going to be really good in 2D systems.
Can I ask a question?
Yeah, go ahead.
So you say this ARPES can give you some many-body effect, right?
Yeah, I'll get to that. Yeah.
Oh, okay.
Yeah.
Good.
So the many-body effect is, basically I'm just kind of telling you, like, okay, ARPES comes in, and so essentially what ARPES does is it measures the energy difference between having n electron in your system and having n-1 electron in your system for a specific momentum. Okay, so, and that's very abstract way of thinking about it, because what if the band structure and what if the energy of the electrons was radically changed by effects deep into the material, by correlation effects, so that it would radically change the energy of plucking an electron out so that it doesn't really align with the band structure that you predicted. Those are what I would call many-body effects in this case. Yeah. So just before we move into a bit more specific stuff, other alternative to ARPES. Since ARPES was introduced and perfected, there's been now a lot of different variation of ARPES that have been going around. So, for example, angle integrated. I think what is that? It's like ARPES, right? But you do it for so many angles, and you have to completely integrate the intensity of the electrons that you get for all of the angles. IPES is the inverse of ARPES, where you will send an electron in. So you need an electron, like an electron gun, with very, very precise momentum and energy of the electrons, and you get the photon out. So that's the opposite. And then a spin result ARPES is, now you want to not only get the electrons coming out, but you want to get the up electrons and the down electrons separately. And that's constructing. That's in the case if the band structure has spin, the spin degrees of freedom is active in the band structure. That's going to be an important technique, and that's been really important in topological insulators. Okay, so the free electron in ARPES, that's an important subject because to understand how well ARPES describes materials, you have to understand the free electron model and how we can come to really have a good hold onto the behavior of metals. Okay, so like Tsung-Chi's question, you asked about insulators, right? We really need to have states at the energy that we're going to probe, okay? And if an insulator has a huge gap usually there, and we're not going to be able to get anything out of there, okay? So what is the free electron model? So it is a metal because we're considering every valence electron again around the atoms and the element to be able to move around freely in the system, okay? And they move freely. It's if you put in a potential difference, there's going to be a clear current going through. It's clear. It's a metal. It has a very small resistivity. And then when they're moving, I mean, these are electrons. They're moving freely. You go back to your classical mechanics, and they're going to be having a dispersion that is just k squared over 2m. So quadratic dispersion for massive particles. That's exactly what you get. They're going to be, if you have just a finite sample, right? There's only n electrons for the number of sites in your system, for the number of atoms. So this finite concentration of the charges defines mu here, the Fermi level, defines the energy at which you're stopping to pile up electrons into your system, right? So since they're fermions, you start putting electrons, and you start putting them at the lowest energy for the k squared over 2m, and then you start piling them up, adding them, and once you've filled out this Fermi C up to the Fermi level, you have your metal. And it is a very idealized model, but you can play this game for complex arrays, right? This case, this is just a square array, but you could play this game for very complex arrays of the free electron model, and you would get, dispersions that have a rich structure in momentum space, but don't have any correlation effect. So the electrons are completely free from each other, and they're just there's no effect of one electron on the other. Yeah, so sorry, go back here. So then there's no effect of one electron onto the other. In general, what technique, like, I might be getting out of my limb here, but in general, with techniques like DFT and ab initio techniques, at least the way as I understand some of them do, is they're able to do a treatment that is beyond this free electron model and incorporate some level of electron correlation into the system, right? They're able to tell you that these energy levels here, these bands, will be slightly renormalized, and it will change the band dispersion of the model. It will not, these are not the same as the many-body effects I will present later, I think. But they will change the band dispersion of the model compared to like a very simple free electron model. So using ARPES, what we actually we measure is the actual dispersion relation of the material. So we're not measuring our theoretical dream, but rather the actual dispersion in the material. And how do we measure this? So what we measure is the intensity of the electrons coming out for a certain momentum k, and a certain energy, well, here designed as a frequency omega, right? So, and this the spectral intensity that we're getting out of the from ARPES is directly correlated to what's called the spectral function, this a here, a of k omega. And the spectral function has always been it's an extremely valuable tool for the theorist, because in the spectral function tells you how much my energy levels, those are the epsilon k here, how much those energy levels have been modified by many-body effects that's coming from the free energy here. And furthermore, there's this other factor here. So if there was nothing here, right, you just get the 1 over omega minus epsilon k minus this factor square. But because of the other factor here, this a of k omega for a specific k will always look like a Lorentzian, where it will look like, right, like a Lorentzian with a width of sigma prime prime, which is the imaginary part of the self energy. So this here, the self energy is something that the condensed matter theorists really want to calculate, because this encompasses all of this, all of the many-body effects on the electronic quasiparticle. It shows you how much the band of the electrons has been renormalized, it has been shifted, and it also shows you that this quasiparticle only has a certain lifetime, and that, you know, after some time, this quasiparticle will kind of break down, and that effect results in broadening, in expanding all of your energy levels so that they look like Lorentzians. Oops. Okay. So just to put that a bit more in perspective, ARPES can really see the difference between a non-interacting electronic system and a clear Fermi liquid system. So in a non-interacting electronic system, the free electron, like I said before, my electronic dispersion is just going to be of the shape something like this is going to be something like ek equals k squared over 2m, right? And for each of the, if I measure the spectral function for that particular dispersion for the free electron system, it's going to be just a series of delta function at each of the at this when the frequency is equal to this energy level. So you just have like very, very sharp peaks and very, very sharply defined states there. However, if you're in this Fermi liquid that has now quasi-particles that have a lifetime, these peaks now broaden and become Lorentzians of their own, and the Lorentzian will change as you change the energy level and the frequency. So there's a lot more information into these lifetime and the shift of the energy level into this. So you can really distinguish between a very easy, very run-of-the-mill Fermi liquid, non-interacting electronic system, and a more complex Fermi liquid in which some many-body effects have been taken into account. All right, I'm not sure if I'm losing people in this. Am I losing anybody? Let's go here. No, all good. Well, everybody's muted, so I don't know if you're talking, but everybody's muted.
I'm good.
Good. Okay.
They're doing good, Victor. Good.
Good. Thank you, Ganesham. Thanks, guys. Okay. All right. So the big example that I really want to outshine here is the example of copper. Okay, just normal copper. This is about as simple of a metal as you can have. Okay, and it has a clear quadratic dispersion. Okay, it's really clean. It's a free electronic system. So if you do ARPES on this, you see here these are my momentum. So this is zero momentum over here, and this is finite momentum as I move along the x-axis. And over here is the energy, okay? So I can really see this beautiful quadratic dispersion, right? I could extract from there the mass of the electron, right? Probably the effective mass you would get. And a very interesting thing is ARPES is so precise in doing this that if you zoom in onto this border over here on the right side, which is this panel over here, you see that the band is actually shifted. Is actually there's a doubling of the band. That's because in copper there's a very, very small spin-orbit coupling. There's a very small, which results in a Rashba coupling, which splits these two, the up and the down spin by just a tiny amount. So ARPES is able to see even that these beautiful quadratic band and the tiny splitting from the spin-orbit coupling. So that really tells you, okay, copper, it's a very run-of-the-mill system. This is really good. Now, it becomes much more interesting if you tackle complex materials, where now other effects can come in and mess around with the physics. So one thing that you can do, for example, in some materials is include the interaction of electrons with phonons in the system. Phonons are fluctuations in the system, periodical fluctuations of the position of the massive ions. And these can have an effect, they can have an effect in modifying the energy of the electrons in your system and also their lifetime. So it creates an effective Fermi liquid that has renormalized dispersion and renormalized lifetimes. So what happens from that is, so this is just a theoretical plot of what you would obtain if you allowed electron-phonon interaction and what that would do to your Fermi energy. So here, here is my Fermi energy. What it would do is it would have a high, the peak would be higher here. As you can see, the color is high. The peak of my dispersion would be higher here. I would have a higher intensity. And then it would be smaller over in this range. And the white line here is just my quadratic dispersion, which looks linear close to the Fermi energy. And you see how it would be radically modified by the electron phonon. You'd follow this red curve. So if you could measure into a material, we could use ARPES and we could see this, we'd see that this is a clear sign of electron phonon interaction that has changed both the position of the bands and the lifetime of the quasiparticles. And lo and behold, if you do this this is the observed ARPES intensity for bismuth 2201, sorry. And I think this is another type of material. The color plot at the bottom is the ARPES data, but you can clearly see that there's a higher intensity close to the Fermi level. And if you follow this green line here, that's the maximum of the dispersion for certain momentum. And you can clearly see that it's renormalized compared to what the bare one would have been expected for this material if you hadn't included electron-phonon interaction. So you see this deviation here, which is the same thing as I shown here. There's this deviation and there's this clustering of states close to the Fermi level over here. And you can see the same thing in here in this bismuth 2201, where it's kind of kinked up and there's more states towards the Fermi level. So it's really remarkable that you can see these effects. You can calculate them theoretically, you can predict them. And ARPES is precise enough to be able to go there and to see that.
Can I ask a question?
Yeah, go ahead, Tsung-Chi.
How do you know it is due to phonon but not other effects?
I mean, you don't really know, right? You can't really ask your material like, hi, is this phonon-based stuff? What you can say is that you can make the prediction that it's electron phonon based. You can compare with the prediction, and the comparison is really good. And you can also say, right, you can know that the material from other experimental probes, for example, thermodynamic probes, that there are significant phonons in this material, and you know the energy of the phonons, so things align with each other. You can do a lot of cross-checking in this case to show that this is due to the phonons. But you're right that like there's always a challenge. There's kind of a philosophical challenge every time you're doing science, theory versus experiment. Is how do you know that the experiment proves the theory? You'd rather know what the experiment shows that the theory, which theories are wrong. You're not really showing which theories are right. You're always showing which theories are wrong.
Yeah.
Right. So there's always going to be a difficulty I think that the challenge for the theorist is an overfitting challenge. It's if you're trying to make up too many theories that you're changing too many parameters, and they all fit the data. Well, I don't know if you really can solve it at this point. Okay, so just before going into superconductivity, ARPES has some very challenging experimental considerations to take into account. So the first of them is you need an extremely clean surface, and any surface change, so deterioration, for example, that's also why you need ultra high vacuum. You need extremely clean surface, flat to the atomic level, and you need it to not be perturbed by anything during the experiment. And this slide here just kind of shows you what happens. This is the measured dispersion in bismuth 2212 just after cleaving the surface. Okay, and after leaving it an hour in different gaseous environments, and it completely changes it. It spreads out everything. It's not clear anymore, right? So you really need a clean surface, a clean shape of the surface, and to keep it into ultra high vacuum, which always maintains it to be extremely challenging to deal with. Usually, so for example, Jack Shakalian, Professor Rutgers, they have an ARPES experiment. And they have a system that's called an in situ system, where they can make the materials in a chamber, cleave them there, make a good surface, and move them all in the ultra high vacuum towards where the ARPES is going to be measured. That way, there's never an exposition to any bad thing. It's always maintained in the same chamber to be able to measure. Another challenging thing is that ARPES does not work under pressure. And we'll get back to that at the end of the talk. It doesn't work under pressure because to apply pressure on something, you typically have to put it in anvils. So you can't really shine light into something if it's stuck between two anvils. So that's always been a problem. And magnetic field, the problem with magnetic field is if you put magnetic field in the material, well, you also put magnetic field in the electrons that are being ejected out of the material. So that's really a complicated thing. If you put high magnetic fields in the material, which is usually what you want to do to get the effects that you want, you'll most likely just have such a high magnetic field and electrons coming out that they'll just like they'll get out and then immediately kind of swirl back and go back into the material. So you're not going to collect anything, and it's going to be really weird or something. So, but what it's really good at, it's compared to theory, like I showed, and it has extremely high resolution now in energy and mentum. So you get a lot of data points that are extremely precise, which is really stunning data. Okay, superconductivity. Let's do a very quick recap of superconductivity. Wow, this figure did not come out as I expected it to be. I should have scaled it a bit smaller. Okay, so what are the two main properties of a superconductor? Superconductor has zero resistivity. That's usually the one that people think the most about superconductivity, right? That's going to be the one that's going to allow us for so many amazing experimental, technological applications. If you could, I always remember this example. If New York City could have superconducting wires connecting its power plants to its energy, where it needs energy in New York, you would not be losing 20% of the energy you're creating. I know my own province of Quebec, we make most of our power in hydroelectric dams up north. They're like 1,000 miles away from the cities, right? So to pass the electricity, the current from there all the way to Montreal, we lose about 50 to 20% of the whole electricity produced to resistance, to just warming up, to Joule's heating, right? So a zero resistivity wire is kind of the technological dream. The other cool effect of superconductivity, and usually the one that like theorists kind of think more about, is called the Meissner effect. That's the ejection of magnetic fields from the compound, and that's the one that creates this kind of quantum locking of this superconductor. You've seen it on the table, right? You have the superconducting train where you can take your superconductor magnet and put it on top of your superconductor and put it on top of the magnetic train, and it stays in this position and it goes around. And it's this really stunning property, and it means that there's all magnetic fields are expulsed, are thrown out of the bulk of the material. And this is all due to the fact that in a superconductor, electrons form effective bosons. So instead of being their usual fermions that go around willy-nilly and don't like to be in each other's bubble, in a superconductor, the electrons now like to pair with each other, and they form together an effective boson. And now if you have bosons, you can put as many as you want into the lowest energy state. So you can just like stack them on and condense them. And the condensation into the lowest energy state is able to get you a flow of current, a flow of current without any resistance. In conventional superconductors, the reason electrons bind together is because there's an effective attractive interaction because of the phonons. And this is kind of a cartoon to show it, is that electrons move around in this big, this array of all of the ions. An ion modification, right? This modification of the position of the ions, the phonon. This phonon here can have an impact on the electrons and creates an attractive interaction between the two electrons. They're not attractive interaction in the sense that they're the two of them together in local space, in physical space, but rather in momentum space, they are locked together and they will kind of go into a dense duo together. So this electron phonon interaction, it's called the BCS interaction, and this BCS model of superconductivity has been was brought in 1950s and is really the only, I would say, the only working model of superconductivity that we have. All the other models are still in the theoretical phase, are still trying to coming out and explain some physical compounds. But BCS is the only one that can really explain conventional superconductors. So why, for example, why niobium superconducts? Well, niobium has phonons, and they're rather large. So the electrons will interact with the phonons, and due to the BCS interaction, they will form effective bosons, which will create a superconductive state. And BCS can predict the critical temperature. This is the actual temperature of niobium, but BCS can predict it, and it's really close. And that's what we call conventional superconductivity. It's phonon-based superconductivity, and we can really get a lot of the BCS theory to understand. So let's just go back one slide here. Are we good on this? Good? Yeah. All right. in terms of ARPES, what are we gonna see for ARPES if we do ARPES on a superconductor? Well, the clear thing that happens in a superconductor is that in a normal metal, you have just occupied states all the way to the Fermi energy, and then unoccupied states. So if I come in with my photon, I can just pluck one out and pluck one in, and I can just, I can move an electron from here. If I give it energy, it's going to go here, and that's easy. In a superconductor, there's an explicit exclusion of states over here. There's an explicit exclusion of states around the Fermi energy called a gap. So that there is no electronic state. There's no electrons of this energy that are present in the system. Why is that? Because all of the electrons of these energies have now formed bosons. So they're not behaving like electrons anymore. They form these bosons, and they're now doing the job of the superconductor. So if you have a superconducting state, you have this big gap here where there's supposed to be no states there. Okay. So if we take this and we apply it to niobium, the one I talked about, what do we see? Well, and 1 second, I'm just, my headset has no battery. Okay. So can you hear me well? Good?
Yep.
Okay, I don't hear you, but that's fine, as long as you can hear me. Okay, so what happens in the case of niobium, the round things are ARPES data close to the energy, close to the Fermi energy at a temperature below the critical temperature and above the critical temperature. And what you see is that there are definitely states, right? There's definitely a number of states at the Fermi level for the temperature that is above the superconducting transition. And for below the superconducting transition, there's now there's a reduction. There's still some finite amount, right? Because you're a finite temperature, it's not perfect. But there's a significant reduction of states at the Fermi level, and there's a pileup of states over here at the edge of the gap. And this structure, right, up this hump and then going down, and a clear reduction of states, that's significant, and that is the signature of a superconducting gap. And just so you know, this is stunning measurements, because each of these points is like what is it, like about about half of a millielectron volt of energy difference. This is very difficult because typically you send the energy of your photons coming in is really large, and you're measuring extremely small changes of energy. So measuring things at such a small energy size was a very difficult thing to achieve, and it came on in the 90s and was a significant experimental breakthrough. So a really cool thing that ARPES can do is that, yes, you can get the energy level versus the energy, the intensity versus the energy, but you have momentum. You have the momentum. You can have a momentum resolution. And what you can do now is you can distinguish between conventional superconductors and unconventional superconductors.
Victor?
What happens in conventional superconductors, like the one we just saw before, the DCS, is that your gap doesn't change which momentum you have for your band. So there's always going to be the same gap. Yes, question. Who's got a question?
Yeah, can you hear me? You cannot hear me.
If you're speaking, I can't hear you.
I am speaking and you can't hear me.
Can you just use the chat to type?
Yeah.
Maybe.
I can't hear you.
I'm on my phone, so.
That's weird.
Can you hear me now?
I cannot hear anybody.
Oh.
It's okay. I can ask later at the end of the talk. Yeah, will do. Yeah. Thanks.
Sure.
I can hear now.
Now?
Yeah, whose question?
So the question that I want to ask about still the ARPES measurement of the superconducting gap. So as far as I understand this, you have these electrons which basically couple across the Fermi surface, right? CK coupling to CK minus C minus K dagger or something like that.
Yeah.
And so, I mean, we are still measuring the electronic effects, but you said like we obtain this gap because they are coupled, and that's why they act like a boson.
Well, I mean, that's kind of, yeah. Really, what's happening is that, you know, like you said, if I write on a simple model for the electrons, epsilon k is my bend dispersion. My electrons will, you know, there's going to be an expectation value of ck up C minus K dagger, right? And
Yeah.
the condensation into that state, the creation of these pairs, the condensation into that state will open a gap of from minus delta to delta. And there's no electrons at that energy because they've all now been coupled into the other one with yeah.
I see. Okay, so it really is momentum space picture.
Yeah, basically creating the gap has stolen electrons from the Fermi level to put them, like if you go here, basically what happened is you stole electrons from this here, from in this gap, you stole them from here to put them over here.
And that's why you have the peak across the.
That's why you have the peak, exactly. So the peak is really because of that, you're stealing them from there because it's now much easier to bind them together than to be there in that gap and bind them to existing.
And this peak is shown in the later experiment that you were showing, right?
Exactly. Yeah. So you're really supposed to see such a gap.
Okay.
Yeah. So not seeing this gap is very different. So let's say if you saw the same feature but you didn't see the gap, it'd be puzzling. There's supposed to be this peak here because that's the condensation of all of these lost states here. All of these lost density of states needs to be piled up somewhere, and it's usually
all right. Okay,
not seeing that is usually the signature of pseudo gap. So
yeah. Okay. Thanks.
Okay, so to go back to momentum in BCS, like the ones we just talked about, the gap is typically S wave. It's spherical. There's no modification of the gap with respect to modification of momentum. In the case of the cuprates, right, the family of the cuprates, copper oxide superconductors, the advanced idea for the pairing is that it's called a D wave. So that means that there's nodal region, there's lines of momentum where the gap is zero. There's no gap there. You would have your normal density of states, normal stuff would be there, but the gap would be finite, you know, at 4 points. It would also change sign, but you can't really see that. The gap would have 4 distinct regions of finite value for the gap and 4 nodes, 4 nodal lines. The reason for that is because copper has mainly one orbital at the Fermi level. It only has one orbital that is playing a main job, and that orbital is the dx squared plus y squared, which is inherently a D wave orbital. The nature of the symmetry in the system for that particular band and orbital is D wave. So the thought was, okay, yeah, it's an inherently D wave. It's going to come to also to the gap. The gap is also going to have that D wave structure. What people did is they studied, and that was one of the first tests for ARPES, is they studied bismuth 2212. This very complicated, right? So bismuth, strontium, calcium, copper, and oxide. What really this material is a bunch of junk between layers of copper oxide. So the layers of copper oxide are really what drives the superconductor in this. It's electrons, one free electron at each copper that is able to move around, and that's the one that really does the superconducting transition. And all of the junk around acts as a renormalizer of the band dispersion as a driver of superconductivity. But really think about it, the reason we call them cuprates is because the CuO2 is the essential part of this. So this material here is has a critical temperature of 96 Kelvin. This is 10 times higher than the niobium we just talked about. This is very large temperature. And this material was thought to be a D wave. It's a cuprate. People thought it was a D wave. So what would you see if you plotted the bend the bend dispersion? This is momentum. This is where the band would cross the Fermi level in blue, and people would have expected that at the node there would be no gap, and at the antinode there would be a gap. Okay, so that's what the D wave idea would be, and let's check whether that actually works. So if you take your ARPES and you measure through cuts in momentum space along this arc, well, you see if you do a cut here, you see that the dispersion goes all the way towards the zero, the Fermi energy. So there's no gap in this case. So this is kind of the opposite of what I said, but there's no gap over here. Okay. No, it's exactly what I said. There you go. Yeah. Node, there's no gap. There we go. So there's no gap over here. But as you move towards this point here, as you move your ARPES like line in momentum space, you move it, and then you see that there's a gap opening, right? There's no states at close to the Fermi level, not anymore. So this is like the x-axis is the Fermi is the energy. So actually the distance from the Fermi energy, and you see that there's no states, there's no peak close to it. It has shifted away, whereas here it's right there at the Fermi level. So this is a normal, and this is what you would expect for just a superconductor that has a gap. So this is really showing you that there's a node here. The gap is 0 at this line, and the gap is finite at this line. You can even do that as you move the angle, right? Let's do like this is the black line here is the Fermi surface, and then as you move from 1 to 15, you move through this angle. As you change this angle, you see that the gap here reduces, goes to 0, and then goes up. And this comes from this series of ARPES plot of ARPES measurements that people do. So the gap closes and then goes back up. And that is really striking. And when ARPES was able to do that, there were other experiments that could tell you that D wave was really a strong hypothesis. But ARPES clearly seeing this really made the point that this is a D wave superconductor. This is a superconductor that has 2 line nodes, and you have to. This changes radically. It could not be a BCS superconductor because a BCS superconductor has an S wave gap. You cannot get a D wave gap from a BCS superconductor. Okay. So, and then the cuprates, I mean, the story for the cuprates after the ARPES measurements became much more complicated because this I need to kind of go a bit in depth with this, but I'm going to skip a bit because we're running out of time. And I made essentially my main point of my talk, which is that ARPES was able to distinguish important features of superconductivity in the cuprates. It was also able to look at iron-based superconductors in much the same way. So iron-based superconductors are a recent family with a high temperature superconductivity, but a bit lower than the cuprates. And in this case, you see that as you move the angle around, the gap size did not change. So this was a new family with a new type of superconductivity. And that was very different from the cuprates. In the cuprates, there would have been zeros in there. In this case, everything goes flat. So ARPES is a really critical tool in going and probing deep into the nature of the electron density of states and of the superconducting symmetry and the superconducting gap. So I'm just going to skip this, but essentially in many cases in the cuprates we have a better idea, but there's many mysteries in the cuprates. In the iron-based, we still have no idea what the symmetry of the symmetry of the gap is. Like, why is the gap perfectly homogeneous as you go around? And knowing these questions is essential because knowing what the gap looks like, it tells you how did electrons actually pair with each other and how did they create this Cooper pair. And knowing that can tell us better how we could probably manipulate these superconductors, and how we could create them, and how we could just understand them better, right? And that's, you know, the next step on the path towards the technological revolution of the superconductors, which has not yet come. I mean, the high TC cuprates are like in synchrotrons and in MRIs, but nothing above that. So the technological revolution of the superconductors has not come yet. And this is just a still from the movie Avatar, where they have a unobtainium, which is the a famed they call it unobtainium because it's unobtainable, right? And it's this material that is in the mountains of what's this, of Avatar, whatever the world is, and that's what they say in the movie. They just say it's a room temperature superconductor. That's why we came across the stars to get it. Because if we found a room temperature superconductor, we'd be very excited. So in conclusion, ARPES is a really phenomenal technique that can explicitly probe the gap. It can have a lot of insight into the exact dispersion relation of the electrons. It can get you the gap symmetry and deviations from theoretical predictions. In cuprate, it's been very useful to actually bring new questions to the cuprates. And in iron-based superconductors, it kind of murkied the questions more than alleviated them. So, you know, maybe we can go a bit further on the road to unobtainium and finally get a better superconductor or a high temperature superconductor. And Tsung-Chi already actually sent me a paper that just came out, I think, yesterday on Nature. So they actually found room temperature superconductor at like 15 Celsius in a material at 150 gigapascals. So this is about the pressure at the center of the Earth. Well, half the pressure at the center of the Earth. But nonetheless, you having under this high pressure, you can have room temperature superconductivity. And what's fascinating is that those materials that are being shown right now to have high temperature superconductivity, room temperature superconductivity, are actually BCS superconductors, electron phonon superconductors. And the reason they're such a high temperature superconductors is because they've been engineered with such a high pressure that the phonon energy, the phonons are extremely strong. They're among the strongest you could ever have. So the electron phonon coupling is extremely large. So there's a high temperature, high critical temperature. So it's kind of a feat of engineering. People predicted these hydrides a while back, and lo and behold, they were found a couple of years ago, and now they go all the way to 15 Celsius. So it's quite amazing. But ARPES can never be used on them because you're using pressure, so much pressure to clamp them that you could never go in and look at the bend structure with ARPES. So that's kind of sad about ARPES. It can't do it. Yeah. Okay. Well, thank you for your time.
So yeah, maybe we can first unmute ourselves, and then just give Victor a big hand. Well done. Way to go, Victor.
Thank you, guys.
So yeah, I mean, you can ask any question now. Maybe I'll go first. So what's the most biggest mystery in, say, cuprate?
The pseudogap. The pseudogap is, if you look at the phase diagram of the cuprates, this is temperature on the y-axis. This is doping. So doping changes where you put the Fermi level into your band structure. The first phase diagram that people drew had antiferromagnetic insulators over here and superconducting domes over here and over here. And that was about it. And then what people found is this region here is called a pseudogap. What happens there is that ARPES is able to see a creation of a gap in the density of states, right? There's something is gapping out. So something is getting out of the band structure, but the system is not superconducting. So there's a lot of theories about what this pseudogap is, and it's actually been a driver of a tremendous search in condensed matter theory. And looking, probing further the pseudogap has actually revealed like 5 other phases in there. There's like a spin glass. There's like a ton of stuff. So the cuprates are actually tremendously more complicated than they were once thought in like 1998, let's say. You know, I think like some people like to think that like the cuprates were solved in the 2000s. I think the cuprates are yet to be solved.
Victor,
Yeah.
so pseudo, just to be clear, so pseudo cap system are those which do have a gap, but the electrons, but the states pile up doesn't exist.
Yeah, actually, a lot of people have been described the pseudo gap as there's a gap, but the objects that you're creating by gapping out are not coherent. So there's no phase coherence between the objects you're creating. So there's some like in some sense you're creating Cooper pairs, but they don't have phase coherence. So there's no condensation and the Bose-Einstein condensate.
I see.
But you are creating the pair, so you're kind of gapping out, but there's no coherence. That's I think the best explanation I've yet to hear about the pseudo gap.
Okay, thanks.
How about iron-based superconductor? Is that all?
Oh yeah, iron-based are a mean bunch because they have a gap that is clear around the Fermi surface. Okay, so if you look at here, this is the momentum on the plane, right? This is momentum, and these are all the Fermi pockets, and the height is the size of the gap. So the gap is like very isotropic, and it's just there. There's a gap. It's almost, you could say, S wave, but it's not electron phonon because the phonons are really small in most of them. In some, I mean, like in monolayer iron selenium, electron phonon might be actually the driver, but in many of them, it's actually, they're probably not anything about electron phonon. So what is creating an isotropic gap is a big question. And some people like to think that they've solved it. I don't think anybody's solved the iron-based, and I don't think anybody's close to figuring out the iron-based. Iron-based were discovered in 2011. They're so young. This is baby. This baby system in condensed matter.
Thanks. Great.
Okay, good. Anybody else?
Good talk, Victor.
Thank you, Ganesham.
Good talk.
All right, thanks guys for showing up.